How to resolve bridge loops. The primary method to resolve and prevent bridge loops is using the Spanning Tree Protocol, STP. If a loop has already formed and is causing a network outage, a broadcast storm, you will need to manually intervene to break the loop first, then implement proper loop prevention measures. 1. Breaking an active loop. Immediate action. If a network loop is currently active and causing severe performance issues or an outage, the fastest way to restore service is physical intervention. Identify the affected ports, look for switches with extremely high CPU utilization, rapidly blinking port LEDs, or interfaces with increasing output drops and collisions. Disconnect cables. Manually disconnect cables from the affected interfaces one by one, starting from the network edge if possible. After disconnecting a cable, wait about 30 seconds to a minute to see if normal network connectivity resumes. Example, check if pings become stable. Isolate the source. Once disconnecting a specific cable restores the network, you have found the redundant path causing the loop. Leave that cable disconnected and proceed to long-term prevention 2. Preventing future loops. Long-term solution. The permanent solution involves configuring network devices to manage redundant paths automatically using protocols and best practices. A. Implement Spanning Tree Protocol, STP, or its faster variants RSTP, MSTP, is the gold standard for preventing loops in Ethernet networks. Enable STP globally. Ensure STP is enabled on all managed switches in your network. Most modern managed switches have RSTP enabled by default. Designate a root bridge. Manually configure a core, reliable switch to be the root bridge by assigning it a lower bridge priority value, example 0 or 4096, where lower is better than other switches. This ensures consistent path calculations. Verify STP status. Use commands, example show spanning tree, to verify that the correct ports are in a forwarding state and redundant ports are in a blocking or alternate state, forming a loop-free logical topology. B. Use additional safeguards. Enhance your STP implementation with these features. BPDU guard. Enable this on edge ports connecting to end-user devices like PCs or printers, not other switches. If a port with BPDU guard receives a bridge protocol data unit, BPDU, from an unexpected source, like a user plugging in an unmanaged switch, the port is automatically disabled, preventing a loop. Loopback detection, LPD. This feature can be used primarily on edge ports to send a loop detection packet and check if it returns on the same port, indicating a loop. It can then automatically block the port. Port fast. Enable this on edge ports connected to endpoints to allow them to transition to the forwarding state immediately without waiting for the full STP convergence timer. This prevents connectivity delays for devices booting up, but should never be used on ports connecting to other switches. Review physical cabling. Regularly review your network topology map and check for any accidental physical loops, such as a single cable connecting two ports on the same switch or between two switches that should only have one link. STP, Spanning Tree Protocol. The Spanning Tree Protocol, STP, algorithm, standardized as IEEE 802.1d, works by creating a single, loop-free logical topology from a physical network that may contain redundant paths. The algorithm uses special messages called Bridge Protocol Data Units, BPDUs, to elect a central point of reference and determine which ports should actively forward traffic and which should be blocked. The algorithm follows a structured, multi-step decision process. 1. Elect the root bridge. The process begins with all bridges/switches in the network believing they are the root bridge and sending out BPDUs. They negotiate to elect a single root bridge, which becomes the logical center of the spanning tree topology. The switch with the lowest bridge ID, BID, wins the election. The bridge ID consists of two parts: bridge priority, a configurable value, default is 32,768. Lower values are preferred. MAC address, the switch's unique MAC address, used as a tiebreaker if priorities are equal. The lowest MAC address wins. 2. Select root ports, RPs. Once the root bridge is established, every other non-root switch in the network must determine the single best path back to the root bridge. The port on a non-root switch that has the lowest path cost to the root bridge is selected as the root port. All root ports are placed in a forwarding state. The path cost is determined by the bandwidth of the links along the path. Higher bandwidth means a lower cost. The switch adds the cost of its incoming interface to the cost received in the BPDU to calculate the total path cost. 3. Select designated ports, DPS, for each shared network segment, link. In the topology, one switch port is chosen as the designated port to forward traffic onto that segment. All ports on the root bridge are automatically designated ports and are in a forwarding state. For links between non-root switches, the port on the switch with the lowest accumulated path cost to the root bridge becomes the designated port for that segment. Designated ports are also placed in a forwarding state. 4. Block non-designated ports. Any port that is not designated as a root port or a designated port is put into a blocking state. These ports do not forward user data, preventing loops. They still listen for BPDUs to detect topology changes and can transition to a forwarding state if an active link fails. STP port states during this process and in regular operation, a port transitions through various states. Forward state purpose duration, default, frames. Disabled administratively shut down. No N/A blocking listens for BPDUs, prevents loops. No max age, 20s, listening processes BPDUs to determine topology. No forward delay, 15s, learns MAC addresses, builds forwarding learning. No forward delay, 15s, table. Forwarding fully operational, forwards all traffic. Yes N/A the entire process ensures a stable, loop-free network with redundant paths available for failover. There are several enhanced versions of the original spanning tree protocol, STP, primarily the Rapid Spanning Tree Protocol, RSTP, and the Multiple Spanning Tree Protocol, MSTP. These enhancements were developed to address the slow convergence time and lack of VLAN awareness of the original 802.1d STP. Rapid Spanning Tree Protocol, RSTP, IEEE 802.1w, is the most widely adopted and is often the default spanning tree mode on modern switches. Its main goal is faster convergence, network recovery, after a link failure or topology change. Key enhancements over classic STP, faster convergence, RSTP typically converges in seconds, often less than a second for point-to-point links, compared to STP's 30 to 50 seconds. Rapid port transition, it uses a handshake mechanism, proposal/agreement, on point-to-point links to quickly transition ports to the forwarding state, bypassing the lengthy listening and learning timers of STP. Fewer port states, RSTP consolidates STP's 5 port states, blocking, listening, learning, forwarding, disabled, into just 3, discarding, learning, and forwarding. New port roles, it introduces alternate and backup port roles which immediately provide a standby path to the root bridge, allowing for instant failover if the primary link fails. Faster BPDU transmission, non-root bridges in RSTP send BPDUs proactively at regular hello time intervals, rather than only after receiving a BPDU from the root bridge, leading to quicker failure detection. Multiple Spanning Tree Protocol, MSTP, IEEE 802.1s, is an extension of RSTP designed for large, complex enterprise networks with many VLANs. It provides the fast convergence of RSTP while adding the ability to manage traffic load balancing across multiple redundant links. Key enhancements over RSTP, VLAN load balancing, unlike STP and RSTP, which run a single spanning tree instance for all VLANs, MSTP allows you to group VLANs into multiple instances. Multiple instances, each instance runs its own independent spanning tree algorithm. This means traffic for one set of VLANs can use one physical path, where a port is forwarding, while traffic for another set of VLANs can use a different physical path, where that same port is forwarding. Regional grouping, switches with the same configuration name, revision number, and VLAN to instance mapping form an MST region. The protocol manages connectivity both within and between these regions. Resource efficiency, by grouping VLANs into instances, MSTP reduces the CPU overhead on switches compared to running a separate STP instance for every single VLAN, a Cisco proprietary protocol called PVST+. Summary comparison of protocols feature STP, 802.1d, RSTP, 802.1w, MSTP, 802.1s, convergence speed slow, 30 to 50 seconds, rapid, seconds or less, rapid, same as RSTP, single instance for all multiple instances, VLAN support VLANs grouping, not possible, single not possible, single load balancing yes, via multiple instances path, configuration simple most complex backward yes, falls back to STP yes, compatible with STP and N/A compatible, mode, RSTP. Modern networks almost universally run RSTP or MSTP to ensure high availability and efficient use of redundant physical links.